Yeah, this is my projectile lab. The purpose of it was to find the effect of air resistance on projectile motion. Overview, we used glow script again and tracker to find a theoretical and experimental. We did two theoreticals, one with air resistance, one without. We found that air resistance caused a shorter flight path due to the negative acceleration it was causing on the ball or the paper ball. The main physics, the velocity update equation, I used this in my glow script. We used it in my glow script because, it's update velocity, right? Acceleration is just force divided by mass because F equals ma. And then air resistance, this is the equation we were given. And I found B later in the thing. So we took a paper ball, which was the system, and we threw it, and then the air, the table, the earth, everything around it was the surroundings. We calculated its initial velocity using the first two frames in tracker. It started at 0, 0, 0, and it's on Earth, so it's 9.8 meters per second force of gravity, and it's moving down. So I just set that as negative. Experimental. Yeah, we videoed the video of throwing a ball straight across. We tracked it each data point, and then it gave us the data which we put into Excel for the graph. We also use that data to find the initial velocity, like I mentioned earlier. On the coding, we set the initial velocity to the 1.6, which we had found. We used the velocity update equation, the position update equation, which velocity updates, as I explained earlier, and the position update is kind of self-explanatory. And then we needed the FNet for the velocity update, so we found it here. And we used the air resistance. So for the first one, B was 0, so I didn't really have to worry about that. And then for the second one, we found B. We had to take an integral there, but I got it. Yeah, because math. Yeah, so we take that. We know force equals ma. We go there. Then we bring mass to the side, and acceleration is second derivative of velocity, so we take the integral of the right side and we get that. Yeah, here are the results. We got the three graphs. Can I zoom in at all? I can't. Oh well. So they all pretty much start the same, which is pretty cool to see. And then as it slowly gets further and further, because of air resistance, it slows down. The experimental had more air resistance than our theoretical 2 did, which is theoretical 2 is the one with air resistance, theoretical 1 was out. Theoretical 1 is just linear the whole time as we expected. The other two are, this is my side. The other two were exponential, but not as exponential as each other, because I guess, here we go. Initial velocity probably could have been a bit more precise, but I think, that looked pretty good. And then the ball is not a perfect sphere in real life. It's not ideal. There's crevices, there's folds, it is paper, it's going to get thrown around by the wind, it's going to move left and right, and throw it perfectly straight. So all those things kind of cancel each other out, and then not cancel each other out, affect it more. And then finally we're at the what if. So what if it was thrown straight up opposed straight to the side? Well, it would take longer, and that's not a point of contention. So I just drew two little things to kind of make it make more sense. Let's pretend these are at the same point on the y-axis. So here it just has to travel y. Right? Here it has to travel up until it's 0, then back down to y, and then the same amount of time it took for it to go from y to 0. And then what is terminal velocity? Well, that's the point where the net force is equal to 0 because air resistance and acceleration cancel each other out. R did not because they were exponential at the end. If it went from linear-ish to really to exponential to linear, that means the net force would be 0, which also means that acceleration would be 0, which means it'd be a linear graph. So it'd go from 0, so it'd be exponential to linear. The model that would show it would be drop it from a very tall height. At some point, it would reach its terminal velocity, and everything would cancel out. The end. Thank you for listening. I think.